Time itself might be an illusion. We are about to journey through 25 of the most astonishing facts about our universe, each one revealing a cosmos far stranger than our daily lives suggest. By the end, your understanding of reality, from the ground beneath your feet to the farthest star, will be fundamentally transformed. We will uncover why black holes could stretch you into a thread of atoms, how the universe is mostly made of invisible forces, and whether everything we see is just a grand cosmic projection. What single idea about space and time already keeps you up at night? Our first mind-blowing fact is that time is not a universal metronome ticking at the same rate for everyone. It is a personal, pliable experience shaped by your motion. This is the core of Einstein's theory of special relativity, a concept known as time dilation. In simple terms, the faster you move through space, the slower you move through time, relative to someone who is standing still. This is not science fiction, it is a fundamental property of our universe. The most famous illustration is the twin paradox. Imagine identical twins. One stays safely on Earth, living a normal life. The other boards a spacecraft and embarks on a journey at a significant fraction of the speed of light, perhaps to a nearby star and back. From the Earth twin's perspective, decades pass, but for the traveling twin moving at such incredible speed, time itself stretches out. Their heartbeat, their thoughts, the aging of their cells all proceed at a slower rate. When the spacecraft finally returns, the Earth-bound twin has aged decades, while the astronaut twin may have aged only a few years. They are no longer identical, separated by the relentless flow of time, or rather, the lack of it. This effect is so real that we must account for it every single day. The global positioning system satellites orbiting our planet are moving at thousands of miles per hour relative to the ground. According to Einstein, their onboard atomic clocks tick ever so slightly faster than identical clocks on Earth. If engineers did not constantly correct for this relativistic time warp, the GPS in your phone would be off by miles within just a few hours, rendering it useless. So the next time you use a map on your phone, remember, you are relying on a technology that must literally adjust for the bending of time itself to function. But this bending of time is just a hint of a deeper cosmic secret, a truth so profound it redefines what the universe actually is. Everything you have ever seen, touched, or known, every star, planet, and galaxy gleaming in the night sky, represents less than 5% of reality. The cosmos we perceive is merely the visible tip of a vast, invisible iceberg. The rest, the overwhelming majority, is composed of two mysterious and utterly alien components, dark matter and dark energy. Picture the universe as a pie chart. That tiny sliver, just 5%, is all the normal matter made of atoms, the stuff of chemistry, biology, and light. 27% of the pie is dark matter. This is not simply empty space, it is a form of matter that does not interact with light at all. It is completely transparent, invisible across the entire electromagnetic spectrum. We cannot see it, photograph it, or detect it with any telescope. So how do we know it is there? The answer lies in gravity. Dark matter has mass, and its gravitational pull is the cosmic glue that holds galaxies together. Look at a spiral galaxy like our own Milky Way. The stars on the outer edges are orbiting the galactic center at tremendous speeds. According to the laws of gravity we understand, based only on the visible mass of stars and gas, these outer stars should be flung off into the void. The fact that they are not tells us there must be an enormous amount of additional, unseen mass holding them in place. A vast halo of dark matter enveloping the galaxy like an invisible scaffold. We can also see its ghostly handiwork through a phenomenon called gravitational lensing. Einstein showed us that massive objects warp the fabric of space-time, bending the path of light like a lens. When astronomers look at massive galaxy clusters, they sometimes see distant galaxies behind them stretched and distorted into faint, luminous arcs. the amount of bending is far too great to be caused by the cluster's visible stars alone. It is the gravitational pull of the cluster's immense reservoir of dark matter that is warping the light, revealing the presence of this hidden giant. Then we have the most mysterious component of all, dark energy, making up a staggering 68% of the universe. While dark matter pulls things together with gravity, dark energy does the opposite. It is a repulsive force woven into the fabric of space itself, causing the expansion of the universe to accelerate. Think of it this way: if you throw a ball into the air, gravity slows it down and pulls it back. But if the ball were governed by dark energy, it would not just keep going up, it would fly away faster and faster. This is what is happening to our cosmos on the grandest scale. Galaxies are not just drifting apart, they are fleeing from each other at an ever-increasing rate, driven by this enigmatic dark energy. So the universe we call home is a place where the familiar is the extreme minority, a cosmic afterthought adrift in a sea of invisible forces we are only beginning to fathom. This shadow universe of dark matter and dark energy forces us to reconsider something even more fundamental, the very nature of the present moment. Our third mind-blowing fact declares there is no universal now. The intuitive idea that everyone, everywhere, shares the same slice of time we call the present is an illusion crafted by our slow, earthbound lives. In reality, what is happening right now depends entirely on your point of view and your state of motion, a direct consequence of Einstein's relativity and the finite, unbreakable speed of light. To understand this, consider a classic thought experiment. Imagine a long train moving at a significant fraction of light speed. You are standing on a platform as it zooms by. At the exact instant the center of the train is directly in front of you, two bolts of lightning strike the train, one hitting the very front end and the other hitting the very back end. Crucially, from your stationary perspective on the platform, these two strikes happen at exactly the same time. You see the flashes of light from both events arrive at your eyes simultaneously. For you, those events are unquestionably in the same now. But what about a passenger sitting in the exact center of that train car? From their perspective, something profoundly different occurs. They are moving at high speed toward the light coming from the front of the train and away from the light coming from the rear. Because the speed of light is constant for all observers, the light from the front strike has less distance to travel to reach them, while the light from the rear strike has to chase after the moving train. The passenger sees the flash from the front first and the flash from the rear a moment later. For them, the lightning did not strike both ends at the same time. The front was struck first and the rear was struck later. They experienced two completely different nows. This is not an optical illusion or a trick of perception. It is a statement about the fabric of reality itself. There is no privileged clock in the cosmos that defines a single, true present moment for everyone. Your now and my now are personal, relative constructs. If we are moving relative to each other, our slices of present time literally tilt and include different sets of events from across the universe. An event that is in the far future for you could be in the distant past for someone else moving at a different velocity. This shatters the classical idea of a single, flowing river of time and replaces it with a vast, static block of space-time where past, present, and future are all equally real, and what you call now is merely your personal perspective as you move through it. It means the universe does not have a present tense, only a multitude of personal experiences of it, woven together by the unbreakable laws of physics. This cosmic relativity leads us to one of its most extreme and violent consequences, a place where the very fabric of space and time is torn apart. Our fourth astonishing fact reveals that a black hole could stretch you into a thread of atoms, a process scientists call, with grim humor, spaghettification. To understand this, you must first grasp the nature of tidal forces. Even here on Earth, the moon's gravity pulls slightly more on the side of our planet facing it, creating the ocean tides. But a black hole's gravity is so monstrously concentrated that this difference in pull becomes catastrophic over just the length of your own body. Picture yourself falling feet first toward a stellar mass black hole, one formed from a collapsed star. As you approach, the gravitational pull on your feet, being just a few meters closer to the abyss than your head, becomes unimaginably stronger. That difference in force is the tidal force. It acts like a cosmic rack. Your feet are yanked downward with vastly greater acceleration than your torso, while your head is pulled less. You are not simply squeezed, you are stretched lengthwise into an increasingly long, thin strand. Every molecule in your body is pulled away from its neighbor in a line toward the black hole's heart. Long before you would cross the point of no return, the event horizon, you would be elongated into a filament, a stream of particles resembling a single strand of spaghetti. This spaghettification happens well outside the event horizon for smaller, stellar mass black holes, making their approach a brief and gruesome end. But the universe holds a strange paradox. If you were to fall toward a supermassive black hole, like the one at the center of our own Milky Way galaxy, the story changes. Because these behemoths are so vast, their event horizons are far larger, and the gradient of gravity across your body at that boundary is much more gentle. You could, in theory, cross the event horizon intact, slipping silently from our universe into the black hole's interior realm before the tidal forces deep inside eventually pull you apart. One journey offers a spectacularly violent death in outer space, the other a quiet passage into an inner cosmos from which no information can ever return. Both scenarios underscore a fundamental truth that in the presence of such ultimate gravity, the human form is as fragile as a thought, and the laws of physics become a slow, inevitable recipe for dissolution. That spaghettifying pull is not a mysterious force reaching out across emptiness. It is a direct consequence of a fifth, foundational truth: the fabric of space-time is real and it can bend. For centuries, we thought of gravity as Isaac Newton did, an invisible force of attraction between masses. But Albert Einstein gave us a radically different and far more accurate picture. In his theory of general relativity, gravity is not a force at all. Instead, it is the curvature of the very stage upon which the universe plays out, a four-dimensional fabric woven together from the three dimensions of space and the one dimension of time. Mass and energy do not pull on objects, they tell space-time how to curve, and space-time tells objects how to move. The classic analogy is a trampoline. Imagine a flat, stretched rubber sheet representing the fabric of space-time when it is empty. Now place a heavy bowling ball in the center. The ball creates a deep, smooth indentation in the sheet. This is like a star warping the space around it. If you then roll a marble onto the sheet, it will not travel in a straight line. It will spiral inward, orbiting the bowling ball in the curved depression. The marble is not being pulled by a magical string. It is simply following the shortest possible path, called a geodesic, through the curved geometry created by the heavy object. That marble's orbit is a planet circling its sun, not because of a force, but because it is rolling along the contours of bent space. This is not just a poetic metaphor, it is precise physics. We have observed this bending directly. One of the most beautiful confirmations is gravitational lensing, a phenomenon predicted by Einstein. Light, although massless, must also travel along the geodesics of curved space-time. When light from a very distant galaxy passes near a massive foreground object, like another galaxy or a black hole, the fabric of space is so warped that the light's path is bent. From our viewpoint on Earth, this can make the distant galaxy appear as multiple distorted images, stretched into luminous arcs, or even a perfect ring of light encircling the foreground mass like a cosmic mirage. We are literally seeing the universe using space itself as a lens, a direct snapshot of the curvature Einstein described. Every time you drop a pen, you are not witnessing a force, you are watching an object responding to the gentle slope in the invisible fabric of reality created by the planet beneath your feet. That bending of light across cosmic distances creates a profound delay, a built-in lag that makes every glance at the night sky an act of archaeology. The stars are not just points of light, they are messages from the past, and the universe itself is a vast historical archive written in photons. This is because light, while incredibly fast, does not travel instantaneously. It has a finite, though immense, speed of 300,000 kilometers per second. When you look at any object in space, you are not seeing it as it is right now. You are seeing it as it was when the light currently hitting your eye began its journey. This delay is called look-back time, and it means every telescope is fundamentally a time machine. Consider our own sun, the anchor of our solar system. It sits about 150 million kilometers away. At light speed, that journey takes roughly 8 minutes. So the warm sunlight on your face, the very image of the sun in the sky, is 8 minutes old. If the sun were to suddenly vanish, we on Earth would continue to bask in its light and feel its gravitational pull for a full 8 minutes before the sky went dark and our planet flew off into the void. We are always living in the sun's recent past. This effect scales up dramatically as we peer deeper into space. The bright star Sirius, the dog star, is about 8.6 light-years away. The twinkle you see tonight left that star around the time many of you were beginning elementary school. The iconic Orion Nebula, a stellar nursery, shows us its glowing gas as it appeared over 1,300 years ago, from an era when civilizations across the globe were in their medieval periods. But the true scale of cosmic time travel becomes staggering when we look beyond our galactic neighborhood. The Andromeda Galaxy, the great spiral smudge visible to the naked eye on a dark night, is 2.5 million light-years distant. The light entering your eyes from Andromeda began its voyage when early hominids were first walking the plains of Africa. We see it not as a contemporary galaxy, but as a fossil from an epoch before humanity even existed. The most distant galaxies captured by our most powerful telescopes are seen as they were over 13 billion years ago, when the universe was in its fiery infancy. We are not just looking across space, we are gazing back through the chapters of cosmic history, watching the universe grow up in slow motion. This transforms astronomy into the most profound form of time travel. We can literally watch the past unfold. By observing galaxies at different distances, and therefore from different eras, we have assembled a cosmic photo album of how galaxies form, collide, and evolve over billions of years. We are not predicting the past, we are directly witnessing it, one delayed photon at a time. It means the night sky is a mosaic of moments, a collage of nows from a million different yesterdays, all arriving together in our present. The next time you look up, remember you are not just seeing where things are, you are seeing when they were, and the deeper you look, the further back you travel. This cosmic photo album of delayed light forces us to ask a deeper question: what is reality actually made of? The seventh mind-blowing fact proposes an answer so bizarre it seems ripped from science fiction. Our three-dimensional universe, with all its depth and solidity, might be nothing more than a hologram. This is not a metaphor. The holographic principle is a serious, though unproven, idea in theoretical physics that suggests all the information contained within any volume of space, like the room you are in or the entire cosmos, could be perfectly encoded on its two-dimensional boundary, like the data on a flat screen. In this view, our rich three-dimensional experience of reality, the feeling of moving through space, the solidity of objects, could be a grand cosmic projection from a two-dimensional surface at the edge of everything. The roots of this astonishing idea come from a profound puzzle about black holes. Stephen Hawking showed that black holes are not completely black, they slowly evaporate by emitting a faint glow now called Hawking radiation. This creates a terrible paradox. If you throw an encyclopedia into a black hole, all the information contained in its pages, the words, the facts, the history, seems to be lost forever when the black hole eventually evaporates into a puff of radiation. This violates a fundamental law of quantum mechanics, which states that information can never be truly destroyed. To resolve this, physicists like Leonard Susskind proposed a revolutionary concept. Perhaps the information from that encyclopedia is not lost inside the black hole. Instead, it is meticulously preserved, scrambled, and encoded on the black hole's two-dimensional event horizon, the surface that marks its point of no return. Every bit of data about the falling object is painted onto this spherical shell like pixels on a vast cosmic sphere. The three-dimensional interior, the black hole itself, is then a projection of that information. This insight was then scaled up to the entire universe. If the information content of a region of space is proportional to its bounding surface area, not its volume, then reality might work the same way. Think of a standard credit card hologram, the little shiny square that shows a three-dimensional image of a bird or a globe. That three-dimensional image is not stored inside the sticker. It is encoded on the flat, two-dimensional surface of the foil. Shine light on it, and the three-dimensional projection emerges. The holographic principle suggests our universe might operate on a similar, unimaginably vast scale. The entire cosmos, with its galaxies, stars, and planets, could be a magnificent projection from a two-dimensional film of information at the farthest edge of space. While this remains a theoretical framework and is far from proven, it is a powerful reminder that our most basic intuitions about reality, about what is solid and what is real, might be the grandest illusion of all. We may be living inside a shadow play, a cosmic story written on a flat surface we can never see. If the universe is a hologram, then the empty stage it is projected upon is anything but quiet. Our eighth astonishing fact reveals that empty space, the purest vacuum we can create, is not empty at all. It is a seething, boiling sea of energy, alive with spontaneous creation and destruction. This quantum vacuum is the most fundamental state of the universe, and it defies every classical notion of nothingness. According to quantum mechanics, specifically the Heisenberg uncertainty principle, there is a fundamental trade-off at the tiniest scales. For incredibly brief moments, energy can be borrowed from nowhere as long as it is paid back almost instantly. This temporary loan allows for a bizarre phenomenon, the spontaneous appearance of particle-antiparticle pairs, often called virtual particles. Imagine the fabric of space at a scale far smaller than an atom. Everywhere and at every moment, pairs of particles and their antimatter twins, like an electron and a positron, flicker into existence out of pure nothing. They exist for a sliver of time so short it is almost impossible to conceive, and then they collide and annihilate each other, returning the borrowed energy to the vacuum. This is not a theoretical fantasy, it has real, measurable consequences. One of the most elegant demonstrations is the Casimir effect. Picture two perfectly smooth, uncharged metal plates placed incredibly close together in a vacuum, separated by a gap smaller than the width of a virus. In the empty space outside the plates, virtual particles of all wavelengths can pop into existence. But in the narrow gap between the plates, only certain wavelengths can fit, like specific musical notes resonating in a tiny chamber. This restriction means there are slightly fewer virtual particles flickering in the gap than outside it. With more activity pushing on the plates from the outside than from within, the plates are gently forced together. This is not magnetism or gravity, it is the direct physical pressure of the quantum vacuum itself, a force generated by the restless energy of empty space. This vacuum energy, or zero-point energy, presents cosmology with its most embarrassing problem, the cosmological constant problem. When physicists try to calculate how much energy this boiling quantum vacuum should contribute to the universe, the number they get is absurdly, catastrophically large. It should be 1 followed by 120 zeros times stronger than what we actually observe. If that predicted value were real, the repulsive force of this vacuum energy would have ripped every atom, every star, and every galaxy apart in the first instant of the Big Bang. The universe as we know it would not exist. The fact that we do exist and that we measure the vacuum energy to be incredibly small but not zero is one of the greatest unsolved puzzles in all of science. It means either our theories are profoundly incomplete or there is a miraculous, fine-tuned cancellation we do not understand. So the void between stars is not a silent nothing. It is a chaotic froth of potential being, a constant reminder that at its heart, reality is built on a foundation of uncertainty and fleeting, ghostly motion. That restless quantum foam hints at a deeper cosmic asymmetry, one that defines the very flow of our existence. The universe possesses a built-in arrow, and it points relentlessly forward. We all instinctively feel the direction of time. You can break an egg, scrambling its ordered yolk and white into a messy mixture, but you will never see those scattered parts spontaneously reassemble into a perfect, whole egg in the frying pan. Memories are of the past, never of the future. This one-way street we call time finds its origin not in gravity or relativity, but in a fundamental law of nature called the second law of thermodynamics. It states a simple, profound rule in any closed system. The measure of disorder, known as entropy, always increases or stays the same. It never decreases. Think of a drop of cream falling into a black cup of coffee. Initially, the system is ordered. The cream is a distinct, swirling blob against the dark background. But watch what happens. The cream begins to diffuse, its tendrils mixing and swirling into the coffee. The once clear boundary blurs. After a few minutes, you no longer have cream and coffee. You have a uniform, light brown latte. The disorder of the mixture has increased dramatically, and it will never spontaneously separate back into distinct black coffee and white cream. That is entropy increasing, and it gives time its irreversible direction. The reason we remember the past and not the future is because the past was a state of lower entropy, more order. Our brains and all recording devices work by taking in orderly information and dispersing energy as heat, increasing the universe's overall disorder in the process. A memory of an event is a highly ordered pattern in your neurons, but creating it required energy that was ultimately lost as waste heat, contributing to cosmic disorder. You cannot have a memory of the future because that would require a decrease in entropy, a reversal of the universal trend. So why does time have this arrow at all? The answer points back to the very beginning. Physicists believe the universe started in an incredibly special, low-entropy state at the moment of the Big Bang. It was an unimaginably hot, dense, but remarkably smooth and ordered soup of energy. From that pristine starting point of high order, the only way for the cosmos to go was toward greater and greater disorder, like a clock being wound up just once at the dawn of time and now slowly unwinding. Every process we see, from the burning of a star to the rusting of a nail, from the growth of a tree to the fading of a memory, is a step along this grand journey from order to disorder. The increase of entropy is what gives time its palpable direction, its irreversible flow. It explains why we see scattered pieces of a fallen vase but never see them leap back onto the table whole. It tells us why youth gives way to age and why the cosmos itself is evolving from a dense, hot beginning toward a cold, diffuse, and uniform end. The arrow of time is not written into the fundamental equations of physics, which work perfectly well if time runs backward. It is written into the specific, low-entropy condition of our universe's birth. We are all witnesses to and participants in the long, slow mixing of the cosmic coffee. The relentless march of entropy shapes a single, unfolding timeline. But what if that timeline is not alone? The ninth astonishing fact shatters the very idea of a singular reality, proposing there could be an infinite number of you, living out every possible version of your life in parallel universes. This is not science fiction, but a serious, though deeply strange, interpretation of quantum mechanics known as the many worlds interpretation. It begins with a fundamental quirk of the quantum world. Before we measure or observe a particle like an electron, it does not exist in a single defined state. Instead, it exists in a blur of all possible states at once, a superposition. Only upon observation does this blur seem to collapse into one definite outcome. The traditional Copenhagen interpretation says this collapse is random. The many worlds interpretation offers a breathtaking alternative. There is no collapse. Instead, at the moment a quantum event occurs with multiple possible outcomes, the universe itself splits or branches into multiple copies. In each new branch, every possible outcome actually happens. Imagine a simple experiment with a single electron. In our world, we detect it spinning in one direction. But according to many worlds, at the instant of detection, reality divided. In one newly created branch, the electron was found spinning that way. In another, perfectly real branch, it was found spinning the opposite way. Both outcomes are realized, but in separate, now disconnected universes. Now scale this up from a single electron to every quantum event happening everywhere, every particle interaction, every radioactive decay, every flicker of a photon. The branching becomes constant and exponential, creating a vast, ever-growing tree of parallel realities, a multiverse. This means that for every choice you have ever faced, no matter how small, there exists a universe where you made the other decision. In one branch, you took that different job you considered years ago. In another, you missed your train this morning. In yet another, you never met your closest friend. But it goes far beyond personal history. Some branches diverged so long ago that the history of Earth itself is unrecognizable. There are universes where the asteroid that wiped out the dinosaurs missed our planet, and reptiles still rule the Earth. There are branches where life never arose at all, and others where it took a completely different biochemical form. Crucially, these are not distant realms in some far-off dimension. They are right here, branches of reality that split off from our own due to quantum decisions. We are forever separated from them because we become entangled with the outcome in our branch. We are part of the universe that recorded one specific result. This interpretation solves the thorny problem of quantum randomness by saying every possibility is 100% real for someone, or more precisely, for some version of you. The cosmos becomes a tapestry of unimaginable diversity, where every tragedy is balanced by a triumph in another thread, and every missed opportunity is someone else's greatest success. It suggests a reality of such profound scale that our entire observable universe is just one leaf on an infinite branching tree. While we cannot visit these other worlds or communicate with them, their potential existence forces us to reconsider our place in the cosmos, not as the center of a single story, but as one thread in an endless, ever-unfolding narrative of everything that could possibly be. This infinite tapestry of possible worlds is woven from the same fundamental threads found even in the darkest voids of space. Molecular astronomy allows us to sniff out these cosmic ingredients, and it has revealed a startling fact. The center of our galaxy smells like a distillery and tastes like fruit. Deep in the heart of the Milky Way, about 26,000 light-years from Earth, lies a vast, turbulent cloud of gas and dust known as Sagittarius B2. This cloud sits near the supermassive black hole at our galactic core, a region of intense radiation and violent forces. Yet within this chaotic environment, using powerful radio telescopes, astronomers have identified the chemical fingerprints of surprisingly familiar compounds. One molecule in particular, ethyl formate, stands out. On Earth, ethyl formate is the ester responsible for the distinctive aroma of rum and the sweet, tangy flavor of raspberries. The discovery that this same molecule exists in abundance within an interstellar cloud is both delightful and deeply significant. It means that if you could somehow take a deep breath near Sagittarius B2, the complex chemical bouquet would carry the recognizable scent of a liquor cabinet and a fruit basket, a bizarre sensory connection to a place no human will ever visit. This is not a quirky coincidence. It is a direct result of how the universe builds complexity. Stars forge heavy elements in their cores, and when they die, they scatter these elements into space. In the cold, dark molecular clouds between the stars, these atoms can meet and stick together on floating grains of dust, forming increasingly complex molecules through simple chemistry. Radio telescopes act as cosmic noses. Molecules in space tumble and vibrate, emitting radiation at very specific frequencies, like a unique musical note for each compound. By tuning their instruments to these frequencies, astronomers can point a telescope at a distant cloud and essentially take a chemical spectrum, identifying what molecules are present without ever leaving Earth. The list is astonishing, from simple water and carbon monoxide to organic molecules like ethanol, the alcohol in beer and wine, and even glycine, a simple amino acid, one of the building blocks of proteins. This tells us that the raw ingredients for life, the very same carbon-based chemistry that makes up our bodies, is not unique to our planet. It is being cooked up in vast quantities throughout the galaxy, in the cold nurseries where new stars and planets are born. The universe is not just a collection of inert rocks and burning gas. It is a sprawling chemical laboratory, pre-brewing the components of biology long before planets form. So the next time you enjoy the scent of rum or the taste of a raspberry, remember you are experiencing a flavor molecule that is also drifting through the galactic core, a tiny, delicious hint that the cosmos itself might be ripe with the potential for life. That galactic raspberry flavor is a hint of chemistry happening everywhere, but on some worlds the physics is so strange it defies our earthly logic. On Venus, the clockwork of day and night runs in reverse. A single day on Venus, the time it takes for the planet to complete one full rotation on its axis, is longer than its entire year. Let that sink in. It takes Venus roughly 225 Earth days to complete one orbit around the Sun. That is its year. Yet to spin just once on its axis, to have a single sunrise to sunrise, requires an agonizing 243 Earth days. If you could stand on its scorching surface, you would witness a sunrise in the west, watch the sun crawl across a perpetual orange haze for about 116 Earth days of daylight, and then see it set in the east after a daytime that lasts longer than a season on Earth. The entire cycle of day and night would outlast the planet's journey around our star. This bizarre situation is compounded by its retrograde rotation. While Earth and most other planets spin counterclockwise when viewed from above the North Pole, Venus spins clockwise. It rotates backwards. The most likely explanation for this cosmic oddity is a cataclysm of unimaginable force in the ancient solar system. Astronomers theorize that a colossal impact, a collision with a protoplanet perhaps the size of Mars, struck a young, rapidly spinning Venus a glancing blow. The titanic energy of that collision did not just slow the planet's spin, it likely flipped the entire planet nearly upside down. Picture a spinning top being struck hard on its side, its axis wobbling wildly until it settles into a slow, reversed rotation. This is essentially what happened to Venus. The impact was so violent it reversed the planet's angular momentum, setting it on its slow, backward twirl that persists billions of years later. To visualize this, think of Earth as a graceful ice skater spinning with arms tucked in, completing a rotation every 24 hours. Venus is that same skater after a catastrophic stumble, now spinning clumsily in the opposite direction, taking an eternity to complete a single turn. This extreme rotation has profound consequences. It means the Venusian surface experiences sunlight for months on end, contributing to its runaway greenhouse effect and hellish surface temperatures hot enough to melt lead. It is a world where time itself is stretched and inverted, a permanent monument to a single, shattering moment from the dawn of our solar system. That cosmic collision which flipped Venus is a local echo of the universe's own violent birth. The faint afterglow of that birth still bathes the cosmos, and within its nearly perfect glow, astronomers have found a blemish so large and so cold it should not exist. Stretching across a vast region of space over 1 billion light-years wide, the cold spot is a profound anomaly in the cosmic microwave background, the ancient light released when the universe became transparent just 380,000 years after the Big Bang. This all-sky remnant is our most detailed baby picture of the cosmos, a snapshot of tiny temperature variations that would later seed the formation of galaxies. For the most part, it is remarkably uniform, but the cold spot stands out like a frozen bruise. Discovered first by the Wilkinson Microwave Anisotropy Probe satellite, and later confirmed in stunning detail by the Planck mission, this region is about 70 microkelvins colder than the average temperature of the background radiation. While that sounds minuscule on the smooth canvas of the early universe, it is a staggering departure. It is not merely cold, it is also surrounded by a strange, hot ring, as if some colossal event created a cosmic crater. The simplest explanation is that it is just a statistical fluke, a 1 in 50 chance occurrence in an otherwise uniform field. But its size and distinctive profile make many cosmologists doubt that answer, pushing them toward more exotic possibilities. One compelling theory suggests it could be the imprint of a cosmic texture. In the frantic first moments after the Big Bang, as the fundamental forces of nature were splitting from one unified superforce, the fabric of space-time itself may have undergone phase transitions, much like water freezing into ice. These transitions could have created defects, knots or tears in the structure of reality. A cosmic texture would be one such defect, a point where space-time is wound so tightly it creates a gravitational well. As the ancient light from the cosmic microwave background passed through this well, it would have lost energy, appearing colder to us exactly as we observe. It would be a fossilized scar from the universe's first split second. An even more radical explanation reaches beyond our own universe. The cold spot could be evidence of a collision with another bubble universe in the vast multiverse. In some models of cosmic inflation, our universe is one expanding bubble in a frothing sea of eternally inflating space. Other bubbles with different physical laws could be forming constantly. If, during its early expansion, our universe had brushed against the boundary of another bubble universe, the energy of that collision would have left a distinct circular imprint on the cosmic microwave background, a cold spot where the two realities touched. This idea transforms the cold spot from a mere curiosity into a potential window into a cosmos beyond our own, a bruise from a fight with a neighboring reality. Whether it is a random fluctuation, a knot in space-time, or a multiverse collision scar, the cold spot remains an open wound in our standard model of cosmology, a silent, billion-light-year-wide question mark reminding us that our maps of reality are still far from complete. The cosmic scars and phantom flavors we have uncovered are woven from particles, but one type stands apart as the ultimate cosmic ghost. Neutrinos are so ethereal they can pass through a wall of lead a light-year thick without slowing down. Born in the nuclear furnaces of stars like our Sun, in the cataclysmic explosions of supernova, and from violent events near black holes, these subatomic particles are almost nothing at all. They carry a tiny, almost immeasurable sliver of mass, possess no electric charge, and interact with ordinary matter through only the weakest force in nature, the aptly named weak nuclear force. This makes them the ultimate escape artists of the cosmos. Right now, as you listen to this, trillions of neutrinos from the Sun are streaming through your body every second, passing through the empty space inside your atoms as if you were not even there. They are doing this day and night, flowing through the entire Earth as effortlessly as sunlight through a pane of glass. To have even a 50% chance of stopping a single, typical neutrino, you would need to build a barrier of solid lead not miles thick, not thousands of miles thick, but 1 light-year thick. That is a wall of metal stretching over 9 trillion kilometers. The sheer impossibility of that barrier underscores just how ghostly these particles are. They are not just passing through air, they are passing through planets and stars as if the universe were made of mist. So how do we possibly detect something so intangible? We build traps of unimaginable scale and wait for a rare, direct hit. The Ice Cube Neutrino Observatory in Antarctica is a perfect example of this cosmic patience. Scientists have drilled deep holes into the pristine ice at the South Pole and lowered over 5,000 sensitive light detectors along strings, creating a grid that encompasses a full cubic kilometer of ice. This immense volume of ultra-clear ice acts as both the target and the detector. On the extraordinarily rare occasion that a neutrino does interact with an atom in the ice, it produces a secondary particle that moves faster than light can travel through that ice. This creates a faint flash of blue light called Cherenkov radiation, a luminous shockwave similar to the sonic boom of a jet. The grid of sensors captures this faint blue pulse, allowing physicists to trace the neutrino's energy and direction back to its violent origin in deep space. Other detectors use similar principles with vast volumes of purified water or liquid argon. Catching neutrinos is like trying to see the shadow of a single, silent moth in a cathedral during a thunderstorm by waiting for it to randomly collide with one specific dust mote. Yet by building these enormous, quiet traps, we have begun to catch these cosmic phantoms. They carry unaltered messages from the hearts of stars and the most violent explosions in the universe, information that light, which scatters and is absorbed, can never bring us. They are silent witnesses to the universe's hidden engines, whispering secrets as they pass through our world and through us without a trace. Our most familiar cosmic companion is quietly slipping away from us. The moon is not a fixed, permanent fixture in our sky. It is slowly but steadily receding from Earth, moving about 3.8 centimeters farther away every single year. This gentle retreat is a direct consequence of the same gravitational dance that creates our ocean tides, a cosmic exchange of energy that is subtly reshaping both worlds. As the moon's gravity pulls on Earth, it creates a bulge of water on the side facing it. However, Earth rotates on its axis faster than the moon orbits around us. This rapid spin drags that tidal bulge slightly ahead of the moon's position. Think of it like trying to pull a heavy object with a rope, but the object you are pulling is slightly off to the side, tugging at an angle. This misaligned bulge, in turn, exerts its own gravitational pull on the moon. That forward tug acts like a gentle but constant accelerator, feeding energy into the moon's orbit and nudging it into a slightly higher, slower path. The energy for this boost comes from Earth's own rotation. Our planet's spin is very gradually slowing down as it loses this angular momentum to the moon. This means our days are getting longer imperceptibly by about 1.7 milliseconds every century. Over deep time, these tiny increments create a staggering picture of our shared past and future. Rewind the cosmic clock by 4 billion years, shortly after the moon formed from a colossal impact with a Mars-sized object. Back then, the moon was perhaps only 15,000 miles away, a looming titan that would have filled a quarter of the daytime sky. Its immense gravitational pull would have generated tides hundreds of feet high, surging across the young continents every few hours. And with Earth spinning so much faster, a day would have been a brief whirlwind, lasting only about 5 of our current hours. The sky would have been a dramatic, violent place, dominated by a terrifyingly close, geologically active neighbor. Now, project that same slow drift forward into an almost unimaginable future. In about 600 million years, the Moon will have receded so far that it will no longer be able to completely cover the Sun during an eclipse. The beautiful symmetry we enjoy today, where the Moon's disk almost perfectly matches the Sun's, is a temporary cosmic coincidence. Future inhabitants of Earth, if any remain, will witness only annular or partial eclipses, a ring of fire around a moon that appears too small to do the job. The silent, steady retreat of our moon is a humbling reminder that even the most stable-looking relationships in the cosmos are dynamic, evolving stories written in the slowest of motions. The ghostly passage of neutrinos is a whisper from the nuclear hearts of stars, but when those hearts finally grow cold, they can leave behind a treasure of almost unimaginable value. Some stars, in their final, silent form, are essentially cosmic diamonds. This transformation is the ultimate fate of stars like our own Sun, a journey from a blazing sphere of plasma to a cold, dense jewel adrift in the darkness. After a Sun-like star exhausts its nuclear fuel, it sheds its outer layers in a beautiful planetary nebula, leaving behind only its hot, exposed core. This remnant is a white dwarf, an object with the mass of a star but crammed into a volume the size of Earth. A single teaspoon of its material would weigh as much as an elephant. For billions of years, this white dwarf radiates its leftover heat into space, slowly fading from white-hot to red, and finally to a cold black cinder. Its interior is primarily carbon and oxygen, the ash of its former fusion fires. As it cools over eons, the theory suggests that under the incredible pressure within its core, that carbon can undergo a phase transition. Just as carbon transforms into diamond under the intense heat and pressure deep within Earth, the carbon in the heart of a cold white dwarf may crystallize into a gigantic planet-sized lattice. The star does not merely contain a diamond; in a very real sense, it becomes one. The most famous candidate for such a celestial gem is a white dwarf officially known as BPM 37093, but nicknamed Lucy after the Beatles' song Lucy in the Sky with Diamonds. Located about 50 light-years away in the constellation Centaurus, Lucy is a pulsating variable star, and its vibrations, like the ringing of a bell, allowed astronomers to probe its internal structure. The patterns of these stellar quakes strongly suggest that a substantial portion of its interior has solidified into a crystalline structure. Based on its size and mass, scientists estimate that if this core is indeed crystallized carbon, it would form a diamond with a mass of about 10 billion trillion carats. To grasp that scale, it is a diamond larger than our entire planet. Picture a single, flawless gem glittering with the cold light of ancient starlight against the absolute black of interstellar space, a monument to a star's brilliant life and its slow, majestic death. It is a reminder that the universe's wonders are not always explosions and collisions, but sometimes the patient, perfect ordering of matter over timescales that dwarf human history, crafting treasures on a scale we can scarcely dream of. That planetary diamond is a solitary jewel in a vast architecture of staggering scale. The largest known structures in the universe are not planets, stars, or even galaxies, but colossal filaments and walls of galaxies, woven into a tapestry cosmologists call the cosmic web. Our 17th fact reveals that galaxies are not scattered randomly like dust in a void. Instead, they form a magnificent, interconnected network with the most immense features known as Great Walls. The most famous of these is the Sloan Great Wall, a staggering filament of superclusters discovered in 2003 using data from the Sloan Digital Sky Survey. It stretches for over 1.3 billion light-years, a thread of tens of thousands of galaxies bound together by gravity. To comprehend that scale, if you could travel at the speed of light, it would take you over 1,300,000,000 years just to go from one end of this structure to the other. It dwarfs any other known collection of matter, a cosmic continent so vast it challenges our understanding of how the universe organizes itself on the grandest scales. This Great Wall is not a solid barrier, but a dense river of galaxy clusters and groups, following the spine of an invisible filament of dark matter. It is part of an even grander pattern. The cosmos resembles a sponge or a neural network. Dense knots where filaments intersect are the richest galaxy clusters. The filaments themselves are the great walls, highways of galaxies, and between these luminous structures lie the cosmic voids, immense, nearly empty bubbles of space that can span hundreds of millions of light years, containing only a few lonely galaxies. This entire web, from the smallest filament to the largest void, is the largest pattern in nature. Its origin story is written in the first moments of time. The seeds were planted by quantum fluctuations, those tiny, random variations in the density of energy in the universe mere instants after the Big Bang. As the universe expanded exponentially during a period called inflation, these subatomic wrinkles were stretched to astronomical sizes. Over billions of years, gravity acted as the master sculptor. Dark matter, drawn by its own gravity, began to collapse into these slightly denser regions, forming an invisible skeleton. Normal matter, the gas that would become stars and galaxies, then flowed along these dark matter highways, pooling at the intersections and condensing into the galaxies we see today. The result is a dynamic, evolving sculpture. You can watch this cosmic history unfold in stunning supercomputer simulations. They start with a nearly smooth, hot soup of particles representing the early universe. As the simulation runs, representing billions of years, gravity pulls the dark matter into a delicate, web-like structure. Luminous galaxies, shown as points of light, bloom like flowers along the dark matter vines, tracing out the filaments and clusters in breathtaking detail. It is a dance of invisible forces and visible beauty. A slow-motion genesis that reveals our universe is not a random scatter of lights, but a highly organized, intricate architecture with each galaxy, including our own Milky Way, residing in a specific neighborhood of this grand cosmic metropolis. The cosmic web connects galaxies across billions of years, but within that vast network, a personal journey could compress an eon into a single lifetime. Time travel to the future is not science fiction. It is a guaranteed outcome of Einstein's physics, a one-way ticket you could theoretically book with a fast enough ship. We have already touched on how time slows for moving objects, but the engineering reality makes this phenomenon breathtakingly personal. Imagine a civilization that masters interstellar travel, constructing a vessel capable of accelerating continuously at a comfortable 1g, the same force of gravity we feel on Earth. This would provide both artificial gravity for the crew and a steady push toward the speed of light. The crew would live normally, eating, sleeping, and watching the stars streak by as their ship's velocity becomes a significant fraction of light speed. For them, time passes at its familiar rate, but back on Earth, clocks tick relentlessly forward. The relativity of time is not symmetrical here because the traveler undergoes acceleration, changing their frame of reference in a way that someone staying home does not. On a round trip to a star a few hundred light years away, the crew might age only a decade or two. When they return, however, they would find Earth advanced by centuries or even millennia. Everyone they knew would be gone, their culture transformed, their world unrecognizable. They would be living relics from a forgotten past, true time travelers who jumped forward by staying still in their own moving frame. Another, even more extreme method involves not speed but gravity. A rapidly spinning black hole, like the one depicted in the film Interstellar, warps space-time so severely that time near it crawls to a near standstill compared to the rest of the universe. Orbiting such a monster for a few hours, while a safe distance from its spaghettifying grip, could mean that years pass for those waiting farther away. This is the ultimate expression of gravitational time dilation, where the universe's most extreme objects become natural time machines. The crucial, sobering point is that this is a journey with no return ticket to the past. You can leap forward, but you can never go back to the moment you left. There is no paradox, no breaking of causality, just the simple, inexorable mathematics of relativity playing out on a human scale. The future is a destination waiting for anyone with a fast enough ship, but the price of admission is everything you leave behind. Our solar system feels like a vast neighborhood of planets, but in terms of raw material, it is a staggering dictatorship of one. A single object, our Sun, accounts for 99.86% of all the mass in the entire system. Every planet, moon, asteroid, and speck of dust in orbit around it, from mighty Jupiter to the tiniest grain in Saturn's rings, collectively makes up a mere 0.14%. To visualize this crushing imbalance, picture a standard $100 bill. The Sun's mass is represented by $99.86. The remaining 14 cents is everything else. Of that tiny change, Jupiter alone takes about a dime. Saturn, Uranus, and Neptune claim a few more pennies. Earth, along with Venus, Mars, and Mercury, are worth less than a single grain of sand. All the asteroids, comets, and the countless moons are just cosmic dust. This is not a system of peers, it is a monarch with an entourage of microscopic attendants. This overwhelming concentration of matter is why the Sun holds such absolute gravitational sway. Every planet, including our own, is not so much a partner in a dance as it is a captive in an invisible leash, forever falling around this central titan. We orbit not because we are significant, but because we are caught in the gentle slope of space-time carved by its immense weight. It redefines our place in the cosmic scheme, not as the center of anything, but as a beautifully complex afterthought, a delicate swirl of leftovers in the magnificent gravitational wake of a star. That solar monarch's gravity can forge worlds of unimaginable violence far beyond our own. A planet exists where the sky rains molten glass in a perpetual supersonic hurricane. This is HD 189733b, an exoplanet discovered in 2005, and it is a textbook example of a class called hot Jupiters. It is a gas giant, slightly larger and more massive than our own Jupiter, but it orbits its host star so closely that 1 year, one full orbit, takes just 2.2 Earth days. This intimate, scorching dance places the planet in a gravitational lock, with one side forever facing the star in blistering daylight and the other in eternal night. The proximity creates a temperature gradient from hellish to merely infernal, with dayside temperatures soaring beyond 1,000 degrees Celsius, hot enough to melt iron and vaporize rock. But the true horror of this world is not just its heat, it is its weather. Observations from the Hubble Space Telescope revealed a surprising fact about this planet. It appears a deep, vibrant blue in color, reminiscent of Earth's oceans as seen from space. This is not a sign of water, however. The azure hue is almost certainly caused by a hazy atmosphere rich in silicate particles, the same minerals that make up sand and glass here on Earth. In the upper atmosphere of this alien world, where temperatures are still a searing 900 degrees Celsius, these silicate particles condense to form clouds. But these are not clouds of water vapor or ice. They are clouds of molten glass, tiny droplets of liquid rock suspended in a scorching sky, and then the winds begin. The extreme temperature difference between the permanent day and night sides of the planet drives atmospheric chaos on an unimaginable scale. Scientists estimate that supersonic winds, screaming at speeds over 8,000 kilometers per hour, race from the day side to the night side. That is more than 7 times the speed of sound on Earth, a force that would make the most powerful terrestrial hurricane feel like a gentle breeze. These winds scoop up the droplets of molten glass from those silicate clouds and hurl them sideways across the sky. The result is a global, horizontal sandblaster. The planet is engulfed in a never-ending storm where the precipitation is not water, but scalding, liquid rock moving at bullet speeds. Any hypothetical probe or spacecraft that dared to enter this atmosphere would be scoured and shredded in an instant, its surfaces polished to a mirror finish before being vaporized entirely. It is a world where the very sky is a weapon, a graphic illustration of how alien and hostile planetary environments can become when pushed to their physical extremes by the simple, brutal mechanics of gravity and heat. The violence of alien weather pales in comparison to the ultimate cataclysm that birthed our cosmos, yet even that story is being rewritten. The Big Bang was not a beginning in the way we commonly imagine it. It was not an explosion in empty space, but the sudden, fiery emergence of space itself, along with time and all matter. For decades, this was considered the ultimate starting gun for reality. But modern cosmology suggests this hot, dense state was not the true beginning, but rather a pivotal phase in a much grander and perhaps eternal cosmic story. The leading framework is called cosmic inflation. Picture the universe in its first incomprehensible fraction of a second, far smaller than a single atom. At that moment, it was filled with a strange form of energy that caused space itself to expand at an exponential, faster-than-light rate. This was not an expansion of things into space, but an expansion of the very fabric of space. In a fleeting instant, a subatomic speck of primordial reality was stretched to a size larger than our entire observable universe today. This inflationary period smoothed and flattened the cosmos, planting the seeds for galaxies. When this energy field decayed, it flooded the universe with the hot, dense particle soup we recognize as the start of the classic Big Bang. In this view, the Big Bang is the moment inflation ended and the hot universe we know began, the afterglow of a more fundamental event. But what came before inflation? Some theories venture into even more speculative territory. The cyclic model, or the idea of a big bounce, proposes a universe with no true beginning or end. In this scenario, our expanding universe will eventually stop, and then reverse into a great contraction, collapsing all matter and energy back into an ultra-dense state. Instead of crushing into a singularity and ending, this collapse could reach a maximum density and then rebound, triggering a new inflationary expansion and a new Big Bang, birthing a fresh universe from the ashes of the old. Our cosmos would then be one link in an endless chain of universes, expanding and contracting in a cycle lasting perhaps trillions of years. Other ideas suggest our universe is just one bubble in a vast, eternally inflating multiverse, where new bubble universes are constantly budding off from a timeless background reality, each with its own random set of physical laws. The common thread is a profound shift in perspective. The Big Bang was not the absolute start of time, but a transformative event in our local cosmic history. It is the earliest chapter we can currently read in the book of the universe, but the preface and perhaps entire volumes before it remain shrouded in mystery. We are left with a humbling realization: the greatest origin story we have ever told might itself be just a middle chapter. That eternal cosmic story may be written in a language of profound connection, where particles whisper to each other across the void. Quantum entanglement is a phenomenon so strange Einstein himself called it spooky action at a distance, and it reveals a universe where space is no barrier to instantaneous influence. The concept begins with two particles, like electrons or photons, that are created together or interact in a specific way. Through this process, they become quantum mechanically entangled, their fates forever linked. Think of them as a pair of magical dice. Individually, each die spins randomly, but because they are entangled, if you stop one die and see it land on a 3, you instantly know the other die, no matter where it is in the cosmos, has also landed on a 3. Their properties, like spin or polarization, are not independent. They are two sides of a single, shared quantum state. The spooky part is what happens when you separate them. You could take one particle in a sealed box to a laboratory on Earth and send its entangled twin on a rocket to a planet orbiting a star 1,000 light-years away. If a scientist on Earth opens the box and measures their particle, finding it spinning clockwise, the fate of the distant twin is sealed at that exact instant. The measurement on Earth forces the twin particle 1,000 light-years away to snap into the opposite, counterclockwise spin. This change happens immediately, seemingly faster than the speed of light, as if the particles are connected by an invisible thread that ignores the vast distance between them. This has been proven in rigorous experiments, repeatedly confirming that the correlation is real and instantaneous. But here is the crucial catch that prevents true faster-than-light communication. No useful information is actually sent. The scientist on Earth cannot choose what result they will get. It is always random. They might measure a clockwise spin or a counterclockwise spin with equal probability. And the scientist on the distant planet, when they later measure their own particle, just gets a random result too. It is only when the two scientists later compare their notes, perhaps over a slow radio signal, that they see the perfect, spooky correlation that every time one was clockwise, the other was counterclockwise. The randomness of each individual outcome means you cannot encode a message like the word hello into the spin of a particle and have it appear instantly light years away. The universe preserves causality, the rule that no signal can travel faster than light, but in doing so, it reveals a deeper layer of reality where separateness is an illusion. Entanglement suggests that at the quantum level, the universe is not a collection of isolated objects, but a single, woven whole. Those two particles, though separated by galaxies, remain parts of one unified system, a reminder that the empty space between stars might be filled with invisible threads of connection, binding the cosmos into a seamless tapestry. The galactic raspberry scent is just a hint of the staggering chemical wealth floating between the stars. Drifting near the center of our Milky Way, the same vast cloud known as Sagittarius B2 holds a reservoir of alcohol so immense it defies earthly comprehension. This interstellar cloud contains billions upon billions of liters of vinyl alcohol, a simple organic compound swirling in a frigid haze over 10,000 times wider than our entire solar system. To visualize that scale, if you placed our Sun at the center of this cloud, the orbits of every planet from Mercury out to the distant Kuiper belt would be a tiny, insignificant speck lost in its unimaginable girth. This is not a cloud you could drink from. Vinyl alcohol is toxic and not the kind found in beverages, but its existence on such a monumental scale is a revelation. It tells us the cold, dark voids between stars are not empty. They are sprawling chemical factories operating on a galactic assembly line. Within these frigid clouds, simple atoms like carbon, oxygen, and hydrogen, forged in ancient stellar explosions, meet and cling to microscopic grains of cosmic dust. Shielded from harsh starlight, they undergo slow, cold chemistry, linking together into ever more complex molecules. Vinyl alcohol is a crucial stepping stone, a precursor that can react with other compounds to form the building blocks of sugars, fats, and even amino acids, the very Lego pieces of life. This means that long before a star like our Sun ignites, before planets even begin to coalesce from a swirling disk of gas and dust, the surrounding nursery is already being marinated in a rich, organic broth. When that new solar system finally forms, these complex molecules, frozen onto dust grains and cometary ice, are baked into the recipe of every newborn world. They arrive via comet impacts and asteroid bombardments, a cosmic delivery service of probiotic ingredients. So that titanic cloud of alcohol is far more than a celestial curiosity. It is a giant vat of potential, a testament to a universe that seems almost eager to mix the cocktail of life. Scattered throughout the spiral arms of our galaxy and others, these molecular clouds suggest the raw materials for biology are a universal commonplace, a standard issue part of the star formation process. The cosmos may not be teeming with life we can see, but it is undoubtedly saturated with the promise of it. patiently waiting for the right conditions on the right world to stir the mixture into something alive. That cosmic cocktail of potential ingredients will one day be stretched beyond all recognition by the universe's most dominant and most mysterious force. In the late 1990s, two independent teams of astronomers made a discovery that shattered our understanding of cosmic destiny. By meticulously studying distant supernovae, the explosive deaths of white dwarf stars, they found something deeply unsettling. These stellar beacons, billions of light years away, were significantly fainter than their distances alone would predict. The only logical explanation was that these supernovae were even farther away than we thought. The universe had not just been expanding since the Big Bang, it had been expanding faster and faster over time. Its growth was accelerating. This was a monumental shock. Everyone had assumed the collective gravity of all matter in the cosmos would act as a brake, gradually slowing the expansion, perhaps even leading to a future big crunch. Instead, we found the universe was stepping on the gas. Something was overpowering gravity itself, and we had to give it a name: dark energy. This is not a substance in the normal sense, but a property seemingly woven into the very fabric of empty space. Think of space not as a passive stage, but as an active participant with an inherent springiness, a constant, gentle pressure that pushes everything apart. The more space there is, the more of this repulsive energy exists, creating a runaway effect. As the universe expands, it creates more space, which creates more dark energy, which drives expansion even faster. It is a self-perpetuating cycle that now dictates the long-term fate of everything. The implications are profound and ultimately lonely. If dark energy continues to dominate, the cosmic future is one of increasing isolation and fading light. Billions of years from now, the acceleration will have carried all other galaxies beyond our observable horizon. The night sky, currently sprinkled with the soft glow of Andromeda and other neighbors, will go utterly black. Our Milky Way will merge with the Andromeda galaxy to form one final giant island universe, but beyond that, there will be nothing to see. All other galactic clusters will have vanished over the cosmic edge, their light forever too stretched and redshifted to ever reach us again. Within this solitary galaxy, star formation will eventually cease as gas is used up or blown away. One by one, stars will burn out, from the brilliant blue giants to the long-lived red dwarfs, until only stellar remnants, white dwarfs, neutron stars, and black holes are left drifting in the darkness. Given enough time, even these remnants may decay through theoretical processes. The universe will approach a state of maximum entropy, a cold, dark, and nearly uniform void where the temperature approaches absolute zero. This is the heat death, not a dramatic explosion, but the slowest and quietest end imaginable, a fade to black on a timescale so vast it makes the current age of the universe seem like a single blink. Dark energy is the architect of this destiny, a silent, repulsive force that makes the cosmos not only stranger than we imagine, but lonelier than we ever feared. That cold, lonely future of dark energy is built from the ashes of a far more creative and violent past. Every atom in your body, from the oxygen filling your lungs to the iron carrying life through your veins, is a relic of that ancient stellar fire. The most profound fact of all is this: we are all made of star stuff. When the universe began in the hot flash of the Big Bang, it was a simple, elemental place. For the first few minutes, nuclear fusion raged through the entire cosmos, but it could only cook the very lightest elements: hydrogen, helium, and a tiny trace of lithium. That was it. Every other element in the periodic table, every piece of the complex chemistry that makes planets, oceans, and life possible, did not yet exist. The universe had to build them, and it needed factories of unimaginable power. Those factories are stars. Deep in the searing core of a star like our Sun, gravity crushes hydrogen atoms together under immense pressure and temperature. They fuse into helium, releasing the energy that makes the star shine. For most of a star's life, this is all it does. But for stars much more massive than our Sun, the story does not end there. As the star ages and runs out of hydrogen fuel, its core contracts and heats up even further, reaching temperatures of hundreds of millions of degrees. Now it begins fusing helium into carbon. When the helium is exhausted, the core contracts again, and carbon fuses into heavier elements like neon, oxygen, and silicon. Each new fuel burns faster and hotter than the last, like a desperate engine revving ever higher. In the final, frantic days of a massive star's life, its interior resembles a layered onion. A shell of hydrogen fusion surrounds a shell of helium fusion, which surrounds carbon, then neon, oxygen, and silicon, all burning simultaneously. At the very center, in a core no larger than Earth but containing more than the mass of our Sun, the temperature soars past 3 billion degrees. Here, silicon atoms are fused into the ultimate ash, iron, and here the star's life ends. Iron is different. Fusing iron does not release energy, it consumes it. The star's mighty engine, which has run for millions of years, suddenly hits a wall. With no outward pressure from fusion to support it, the iron core collapses under its own immense gravity in less than a second. This catastrophic collapse triggers a titanic rebound, a shock wave that blasts the star's outer layers into space in one of the most energetic events in the cosmos, a supernova explosion. The violence of that explosion is so extreme that for a few fleeting moments, it creates conditions even more ferocious than the star's core. In this maelstrom of energy and neutrons, every element heavier than iron is forged: gold, silver, uranium, the iodine in your thyroid, all the exotic metals that grace our technology and jewelry. The supernova then scatters this newly forged, enriched material across light years of space, seeding the surrounding cosmic cloud with the raw ingredients for new stars, new planets, and ultimately new life. Our own solar system coalesced from just such a cloud, a recycling bin of stellar debris from generations of stars that lived and died long before our Sun was born. So when you look at your hand, you are looking at a collection of atoms that have journeyed across the galaxy and through time. The calcium that strengthens your bones was forged in a star that died billions of years ago. The carbon that forms the backbone of every molecule in your body was cooked in a stellar furnace. The nitrogen in your DNA, the oxygen you are breathing right now, all were gifts from stars that ended their lives in spectacular violence. We are not just living in the universe as passive observers, we are a vibrant, conscious part of its ongoing story. The universe, in a very literal sense, became aware of itself through us. We are a way for the cosmos to know itself, built from the very elements it spent billions of years carefully constructing in the hearts of its most brilliant and catastrophic creations. From the personal flow of time to the shared atoms in our bones, these 25 glimpses have painted a universe of breathtaking paradox. Time bends, space warps, and our solid reality may be a grand projection. We have navigated a cosmos where darkness reigns, where particles whisper across light years, and where the past is perpetually on display in the night sky. Each fact peels back a layer of the ordinary to reveal the extraordinary machinery beneath. The true revelation is not any single detail, but the collective portrait they form, a cosmos that operates on principles far stranger than our intuition, governed by forces we cannot see, and filled with connections we are only beginning to map. This journey underscores a humbling and beautiful truth. Our everyday experience is a tiny, special case in a reality of infinite variety and scale. We are transient witnesses to a story 13.8 billion years in the telling, built from stardust and animated by the same laws that spin galaxies and stretch the void. So the next time you step outside and look up, remember you are not just looking at points of light. You are gazing at a holographic projection, a tapestry of cosmic history, a network of quantum threads, and a future racing toward isolation all at once. You are part of the mystery. Now we want to hear from you which of these 25 facts reshaped your understanding of reality the most. Was it the phantom pull of dark matter, the infinite branches of the multiverse, or the simple, stunning fact that you are made of star stuff? Let us know in the comments below. If exploring the universe's deepest secrets left you hungry for more, be sure to subscribe. Our journey through the cosmos has only just begun.